Jet propulsion can be defined as the force which is generated in the opposite direction to that of a discharge of fluid under pressure escaping through an opening. The force that makes a lawn sprinkler, similar to the one shown here, rotate when water flows through it is one example of jet propulsion that is readily apparent in everyday life. And the thrust that sends rockets, like this one, into space is another, which is perhaps not such an everyday occurrence. Whatever the form that the device utilizing jet propulsion takes, it is essentially a reaction engine, which operates on the principle of the third law of motion, as stated by the English physicist Sir Isaac Newton in 1687, which is that every action has an equal and opposite reaction. The first recorded use of a reaction engine was by Hero of Alexandria in 250 BC. Hero's engine, a representation of which is shown here, consisted of a sphere into which steam was introduced under pressure. The steam was fed through apertures in the centre of the bearings upon which the sphere was allowed to rotate. Allowing the steam to escape through nozzles in two bent tubes mounted opposite one another on the surface of the sphere created thrust, which caused the sphere to rotate around its axis. It's alleged that Hero invented his engine while he was investigating different methods of opening the doors of a temple in Alexandria. In recent times, one of the first attempts at creating jet-powered aircraft resulted in the development of a hybrid design. An Italian, Secondo Campini, designed a system whereby an external power source, in this case a conventional piston engine, powered a compressor. The output of the compressor was mixed with fuel, the mixture of air and fuel ignited, and jet thrust resulted. Campini collaborated with the Italian aircraft manufacturers Caproni, and in August of 1940 the Campini Caproni CC2 flew. Although the Italians were unaware of it, a year earlier than this the Germans had flown their version of a jet aircraft, the Heinkel 178. This aircraft was powered by an engine designed by a young German scientist called Hans von Ohain. Despite the relatively sparkling performance for that era, it could travel at speeds in excess of 400 miles per hour, the German Air Force initially paid it scant regard, and it was never produced in any quantity. On the 8th of April 1941, the first official flight of the Gloucester E-2839 aircraft took place at Brockworth in Gloucestershire. Sir Frank Whittle had submitted patents for his jet engine in 1930, but it was not until 1939 that sufficient financial and technical backing was found to enable him to manufacture a flyable version of his engine. The firm of Rover had, reluctantly, initially been contracted to produce the Whittle engine, but Rolls-Royce, who could see its potential, eventually took over development of the engine, one of which is shown here. Rolls-Royce reworked the Whittle design to produce the Derwent engine, an example of which is depicted here. This engine was capable, in its Mark IV version, of producing 2,450 pounds of thrust. Later versions of the engine, capable of 3,600 pounds of thrust, were used to power the Gloucester Meteor F8, like the one shown here, flying at an open day at Royal Air Force Kemble in the year 2000. During a visit to the United States in early 1944, the leader of the Rolls-Royce design team found that General Electric were developing engines capable of producing up to 4,000 pounds of thrust. As a response to this, after his return, he initiated a project which culminated in the Nene engine, which at the time was the most powerful engine in the world, with 5,000 pounds of thrust. Possibly one of the most important but least publicized uses of this engine was its incorporation into the Russian MiG-15 aircraft, which was so effective in the Korean conflict. One critical difference between the German engines used in the Heinkel and the later Messerschmitt 262 and those developed from Sir Frank Whittle's original engine was the type of compressor employed. While the Whittle engine used a centrifugal compressor, similar to the example shown here, the German engines, like the BMW 003 model used in the Heinkel 162, utilised an axial flow compressor, similar in design to the cutaway model shown. Axial flow compressors have several advantages over the centrifugal compressor. For instance, whereas the centrifugal compressor compression ratio is limited to approximately 12:1, when the maximum of 2 stages are used in series, by adding more stages to an axial flow compressor, compression ratios as great as 40:1 can be obtained. The term compression ratio refers to the ratio of the pressure at the outlet of a compressor to that at its inlet. A second advantage of the axial flow compressor, almost as important as the first, is that the mass flow which can be obtained through an axial flow compressor is potentially much greater than the mass flow which can be achieved through a centrifugal compressor. As a consequence of these factors, the development of the early centrifugal compressor engines was subjugated in favour of the advancement of the axial flow compressor engines, which continues today. The principle of the gas turbine engine is basically the same as that of the piston engine propeller combination. They both propel a mass of air backwards. Mass times acceleration equals force. In a gas turbine engine, the mass, m, mentioned in the equation, is the air delivered by the compressor. The acceleration in the equation is the difference in the outlet velocity of the air, VO, to that of its inlet velocity, V1, due to the addition of heat energy. Force equals mass times V0 minus V1, which equals thrust. With the piston engine propeller combination, the propeller drives a relatively large mass of air backwards fairly slowly, while the gas turbine throws a small mass of air backwards relatively quickly. Newton's third law states, for every force acting on a body, there is an equal and opposite reaction. In the two cases quoted earlier, the piston engine propeller combination and the gas turbine engine, the force created by the mass of air being thrown backwards and its velocity generates a reaction in the opposite direction, driving the aircraft forwards. It must be remembered that the jet reaction does not result from the pressure of the jet on the atmosphere. In all instances, the resultant reaction or thrust exerted on the engine is proportional to the mass or weight of the air expelled by the engine and the velocity change imparted to it. The working cycle of the gas turbine engine is called the Brayton Cycle, after George Brayton, an American mechanical engineer who invented the continuous ignition engine, which was the basis of the gas turbine engine. The Brayton cycle and the working cycle of the four-stroke piston engine, the Otto cycle, are very similar, as can be seen in this diagram. The induction, compression, power, and exhaust strokes of the Otto cycle are each matched by induction, compression, combustion, and exhaust stages in the Brayton cycle. One major difference, however, exists, in that in the gas turbine engine, combustion, theoretically, occurs at a constant pressure, whereas in the piston engine it occurs, once again theoretically, at a constant volume. Power is developed in the turbine of the engine. Other differences between the piston engine and the gas turbine engine concern the continuous manner in which these processes occur in the gas turbine engine, as opposed to the intermittent procedure occurring in the piston engine. In the piston engine, only one of the strokes is utilized in producing power. The other three are effectively absorbing power, while in the gas turbine engine, the three idle strokes have been eliminated, thus allowing more time for the burning of fuel. This is just one of the reasons why the gas turbine engine has a greater power-weight ratio than the piston engine. The pressure-volume diagram shown here, otherwise known as the Brayton cycle, represents the working cycle of the gas turbine engine in its simplest form. Air at atmospheric pressure enters the engine at point A and is compressed along the line AB. Fuel is added in the combustion chambers, which is signified by point B, and the mixture is burnt, in theory at a constant pressure. In fact, the reduction in pressure shown between points B and C indicates that pressure losses do actually occur in the combustion chamber. The drop in pressure is created by the need to produce the swirl and turbulence necessary for efficient combustion, and this causes a pressure drop throughout the combustion chamber length of between 3 to 6%. Notwithstanding this drop, a considerable increase in the volume of the air is generated within the combustion chamber. Between points C and D, the gas generated through combustion expands in the turbine, where mechanical power is extracted from the energy in the gas stream, and the jet pipe, where the remainder of the gas stream energy provides a propulsive jet as it is discharged. In theory, the gas stream pressure attains a value equal to atmospheric pressure before being ejected.